Hello, everyone. Hello, I think we're live. Welcome, everyone. I'm John Ball, the CTO and founder of Padding. And today I'm going to look at one of the side effects that came out of our NLU research and engineering. And it's how do you use context, how do you store context in such a way that you can bring it back later on. I'm not sure if any of you were watching the Web Summit 2022 the other day. On the third day of it, it was in Lisbon, Portugal. Gary Marcus was running an interview with Noam Chomsky, and both of the guys were talking about the enthusiasm for today's AI technologies. And one of the points that came out was that cognitive science is one of the missing ingredients. I think Gary Marcus put it that there's a lot of nice toys out there, but we need to work on the science, which is underpinned by cognitive science, which I would call brain science. So let's get on with it. So today's focus is on what the enterprise storage solution will look like in the future. Today I would describe it as a system where, let me just change that. I describe the enterprise solution as a system where we're using the 1960s computer technology. You store text, which is some sort of encoded format. You know, you've got your ASCII or EBCDIC, whatever it happens to be. You're encoding information and you're storing it in a file, and then you push that file out into the internet these days, and then you bring them in and you can do analysis on it. But that's very different to what should be happening, which is rather than storing text, which is a language by language specific format, convert that text into its meaning, a lossless representation. And then by putting that out on the internet, you've got access from any of the world's languages to what's just been written. And so you can imagine that you're reading your New York Times in 5 years' time, and you're reading it in Portuguese because you're a native Portuguese speaker, and the same document would be read by somebody in New York in English, if you can call New York speak English. So the goal, and I've seen this come up a couple of times in the last couple of weeks now. If you can take information and store it once and then use it forever, you're definitely on the right path. And if you think about today's deep learning examples, for instance, if you take a current document and you store it in some format that deep learning can give you access to, it's going to be language specific. So if in the future you wanted to have a solution that's working on deep learning, you need to have hundreds or thousands of those databases set up for each of the world's languages. And you can say, oh, but you could translate them each on the fly. Well, I've never seen an accurate translation through one of those statistical translators yet, because they're leaving out the context of the discussion. And if you think of it, conversation is the ultimate test of understanding. If you can speak to me in English, you can probably describe just about anything that anybody's ever discussed, from physics to literature to politics. And you can't get that level of discussion today with the technologies, because they're leaving out the elements of linguistic science. And probably you can see at the bottom here, I'm saying that you can't see that. Let me just do some magic here. You can see here that the change that I'm going to be describing is we don't use parts of speech. That was a great idea Bloomfield brought in the 1930s and hasn't enabled systems to scale. It blocked parsing back from the 1950s up until when people gave up on it in the 1990s and went to full-on computational models. But the other thing that we're basing the work on is the fact that I produced pattern theory, a brain-based theory, and in 2012 I discovered this amazing linguistics model called role and reference grammar that explains how the world's languages work, the world's diverse languages work, and map their syntax into a common meaning representation. And you know, a bit of a spoiler here for the rest of the presentation, but that meaning representation that RRG produces is this lossless format, which you can then use to store your knowledge in such a way that you can then do that magic that I described. A couple of reference books. Here's the Gary Marcus book, which rebooting AI. I think it's got a lot of good examples of what we need to do to solve AI problems. And then this one on the right, it seems to be underutilized in the same way that role and reference grammar is. Sebastian Loebner is a colleague of Robert Van Velen, who's the RIG primary developer. And in Loebner's book, he describes the history of semantics and then explains a bunch of things that people just aren't taught. So my backstory here was as a cognitive scientist in 1983, when I was at university, my professor said we're never going to be able to understand human language. And that was the challenge for me. I then dedicated, well, unfortunately, the rest of my life to this point on solving that problem, thanks GDK. But the reason why she said it was so hard was just because we can't understand the brain. It's not something that's possible, and there's a lot of components in the cognitive sciences that come together to make all of that work, and semantics is another one. And my question to today's students is, why is it that your teachers aren't describing RRG semantics, and there's so much of this push on this new technology, which for the great things it does, fantastic, but for the things it doesn't do, surely you should be covering that in your courses. Okay, so let's go into the first problem. And here, this does come out of Gary Marcus's book, Rebooting AI, and Ernest Davis is his co-author. And it really illustrates the problem of these high-level knowledge graphs. And I know in industry, knowledge graphs are used, which are really properly defined, like a database model. You've got all of these elements that are nested and so forth, and it all hangs together, but it's really a database. And the question would be, how can you take a nice database and convert it into this generic form that can be described by any of the world's languages? So here's an example. I'm going to focus on this word cook here for today. So you've got here an oven, and we've got this arbitrary definition that says an oven is used for cooking, right? So the word cook is written there, and what does cook mean? Well, it's this act where you prepare food, presumably. And notice here, cook is a blank. Let's change that. Now you can't see it because it's too small, but anyway, cook is a person. So now we've switched from the meaning of cook, which is the act of cooking, to cook, which is the person who does the act of cooking. So let's just drill back to that. I'll have to put my head somewhere else. It's getting in the way. And then we've got that this person is capable of cooking, going this other way, and then at a location of a restaurant. So now the system's really falling apart, because cook means two different things, and now a cook, the person, is at a restaurant. So if you work for an airline and you're in a hangar and you've got all of your equipment there to produce meals for the planes, let's just say, then by this definition, you're no longer a cook. So you can't have these constraints that are thrown in. And what's the obvious point here? Well, this is a semantic network, which is general things, but we're putting contextual constraints on it. So it's true that some cooks that work in restaurants don't work in hangars, but that doesn't mean that all cooks work in restaurants. It means some cooks work in restaurants, which is context, whereas all cooks cook in maybe a kitchen, maybe not. So you need to be very careful about how these things work. So let's now go into what the system can do and just go into reinforce it. So what I'd like to do today is I'll show you some theory. I'll talk about the issues. I'll then show you a working version of something that then inspires us to come back to what the industry looks like. And by the way, I will cover some technical stuff. I'm also going to cover the industry side of things. So what is it that we need to do to get this deployed generically? And then we'll just keep reinforcing that. Universal syntax. Hi, Steve. Yeah, definitely not. So the universal part is the semantics, and the world's diverse languages have lots of different ways in role and reference grammar to link into that semantic network. English has one method, and I showed one of the breakthroughs that came out of role and reference grammar in an article, I think at the beginning of this year, where English has this concept of adjectives, but if you build that into your universal semantic model or into your knowledge graph, you're stuck with this adjective thing that then doesn't work for a very large chunk of the world's languages. So English, we use adjectives. In another language, I can't remember which one, all of those adjectives are verbs, and you put like a clitic on top of it. So you just say that this verb is now the adjective state form. And in another language, you use a noun form, and you say this noun is now this adjective type word. So if you don't get your alignment between the language and the semantic network, you've got some problems. So here we've got, hey, Mr. D.L. Thomas, looks like a triples framework. So definitely not triples. In ROG, you finish up with each predicate that has only 2 arguments. And you can have a causation. I'm going to get into an example of that, so I'll come back to it shortly. So here's ConceptNet, and notice that ConceptNet was the diagram that I showed a moment ago, that this is a typical connection between these entities with some type of relation. And so we've got this is a relation here. We're saying ConceptNet is a semantic network and a knowledge graph. And then we've got this thing, which looks a little bit arbitrary, is used for natural language understanding, yeah, potentially. But there's no bidirectional link. It's not clear that natural language understanding uses ConceptNet or how that reverse link works. We've got a made of, which seems like a pretty good generic semantic element. Has-a definitely looks like a semantic element. So is-a is the hypernym association, has-a is a meronym association. And then we've got properties and motivated by goals. So the challenge here would be if we are going to describe language, how would you put those in a sentence? And then is there a better way of putting that sentence into this representation? So let's have a look at the system. I'm going to be using the word feed, so I'll show you how we've just set up one of the predicates in the system. Is that too small to see? Maybe I'll make that a little bit bigger. And I can't read the screen and do this at the same time. So we've got a semantic element here called p:feed to show us that it's a predicate. We're just using that as an icon, and then we're saying it's a predicate type because whether you're using feed as a noun or a verb, it's still going to have this same ability to carry meaning. We're saying it's an activity, which is one of the ROG building blocks. There's 3 associations that we're using in the semantic network. Effectively is, has, and does. So is the hypernyms, has is the meronyms, and does is a selectional restriction. So we don't normally teach this in linguistics this way, but this is the system that I'm using, and at some point I'll push it a little bit harder. There's a bunch of other associations here, but you can see we're using a hypernym in order to do our associations. And you would say, oh, you've made a mistake because you've used the same hypernym twice. And yeah, I recognize that. We've converted to a simpler form to build our phrases out. So now we'll go into the conversation engine. I'm just going to load a sample file here. I think this is our goal, this exchange class. I've shown it before, but let me just run through it and try not to get too distracted by the voice synthesizer that's running at the same time. I'll make that a little bit bigger still. So you can see it's gone through all of that question and answer work. And I'll just go back to the top here. We've got the man bought a car from the dealer for $1, and if a statement's added, we're entering that into context. So that's our knowledge graph implementation. We're simply taking the representation of that meaning and storing it in our knowledge graph, super knowledge graph. So it's lossless. And then we're asking questions: who sold the car? Who received the car? If we look at the current context here, you can see that we're not simply storing the man bought a car from the dealer for $1. The meaning of that includes these other meanings. It's an exchange. It's a reasonably complex example, but there's an exchange of goods when you buy something, and there's an exchange of money when you buy something, and the directions are important. And in that example, if you buy a car from a dealer, then the person who sells the car is the dealer. Even though it's not specified in your knowledge graph representation, because we're using the meaning of buy, which is that have transfer. Who received the car? Received is the type of possession. Again, it's one where you don't have something and then you do. Pay is the focus on the money part of the transfer. So basically, you can see who was sold the car. You can see that regardless of the words, the knowledge graph representation, the lossless format is coping with the fact that we're using different words to put focus on different elements of the transfer. So there's pay. Notice here when you say, did the man pay Beth for the car? We just respond with know the dealer. So you have to know in your answer that it wasn't Beth that was paid for the car, it was the dealer. And so we're substituting in know the dealer. Those types of things, I think, make our communications much more natural. So what I'm showing here is that you've got this amazing generalization that's possible with language. We've got a very simple representation, simple-ish, in that we've broken down the meaning of something into a form that we can then access it from different predicate classes, but it still has the same elements in it that we're manipulating. And then you can use it in conversation. So that's my introduction to the knowledge graph benefits here. Let me just move on to a couple of other resources. We've got cooking. This is coming from Wikidata, and cooking isn't shown as cook in this database. It's actually using the cooking word, and so cook and cooking in Wikidata is a different concept. And then we've got what I would think are a bunch of different associations that are correct in some contexts, but not generically. So this semantic network is combining the context of all of the world's use of that particular word into a semantic network where it's unclear which elements combine to which other elements. And, pictures and, location is kitchen or workplace. That's going to work in some contexts and not in the others. What pattern theory does is it brings this concept of the general, so semantics is a general form of context. And in computers, we take general elements and we then force specific elements into them. So you define your schema and then you put your database records in. That's general schema, specific database records. Pattern theory works the other way, to say that the brain is working from all that we can experience, all we can ever experience is context. So if you've got context coming in, the brain is then making sense of it and producing some sort of semantic network that's combining these meanings and then learning from them and generalizing. So that's cooking. And then if we look at cook, again in Wikidata, you can see there's a whole bunch of names here: Cook County, James Cook. If we click on this one, cook, it's the occupation. So this is the cook person. So it's saying it's a professional, it's a catering profession. That's very detailed. And these things, in Wikidata's case, just grow exponentially large. Not just because it's very random how you're going to add content to the semantic network, because every context you can now start to put semantics in, but also multiple languages. So we're taking something that I would argue doesn't work that well for English and then adding all of the world's languages to it. And now you've got a very big database, but whether you can make much good of it in the future is questionable. Okay, so let's get back on track over here. So there's our goal today. And let's just bother you with one more look at semantics. So when we say cook, here's what the semantic representations are. I'll see if I can make it smaller and still allow you to see it. How do I do that? This one. Okay, so here we've got the food is cooked. The semantic representation for that is the predicate is cooked. If you did linguistics at school, you would think that the verb is, so that's your predicate. But no, in RIG, the meaning carrying element is cooked, and is providing tense. The food is cooked, the food was cooked, the food will be cooked, so past, present, future. So cooked is the predicate here, and the food is its argument. If the food cooks, notice that it's a change of state. The food is uncooked at the beginning and then it becomes cooked. So there's your adjective form, which is the pure state. Here's the verb form, which is what's called an accomplishment, because there's a change of state that takes place over time. Food isn't instantly cooked like a balloon is instantly popped. And then we've got causation. The cook cooks food. So here's the cook doing something which causes the food to become cooked. So it causes that accomplishment to happen, become cooked, the food. And the word "the" actually is a discourse pragmatics word. I've just written it in there and then not here, just to confuse you. And then the last example, the cook, as a referent, we're actually describing the cook as the person who does the cooking. So if I still can't get my head out of the way, but we've got here that the cook is the thing causing something to become cooked. So when you say cook, that's what it always means in terms of that particular predicate. I think I've lost my audio there, Beth. Oh, did I lose my audio? Not sure. Okay, so there's our semantics, and you can go on and on. I only have highlighted a couple of these knowledge graphs. So let's have a quick look at this question. With math, you have to introduce a translation layer, a lookup table, with an array of DBs through the data. Though the data type is harder to work with, something is open readable by humans. So yeah, the knowledge graph as it's currently implemented is a computer solution, and the brain isn't quite the same as that. So when I'm describing the super knowledge graph, I am describing it in terms of something like Vatical type DB, where you're taking things, converting it into a knowledge graph representation, and then persisting it. But in terms of using it, you don't want to have a whole array of distinct databases, which you then have to sort through all of them to find out the correct answer. You actually want random indexing into any of these knowledge graphs that come out. So once you recognize something in that knowledge graph, you need access to every one of its associations. So for that reason, when I'm showing you the system that we use, we've actually loaded everything into memory, and we're simply manipulating memory so that we're not just creating a paging nightmare where all of our information is stored and we're just constantly paging things in and out. It's just too slow for that. Was there another question on that, Steve? Did I answer your question? Okay, so let's just look at a couple of other knowledge graphs to belabor the point about the semantic and context distinction. And my solution to that up here, I've got database normal forms, 1st to 6th. I learned that when I studied computer science. The fact that you need to store databases in a particular way to get full advantage of them. And the same type of thing, I think, would apply to knowledge graphs. And maybe it's a bit early in its life cycle to have done that yet, but I know people like John O'Gorman, he's talked about some of the rules, and probably his principles should be the first normalized forms that we work with. But I know one of them was you don't put in these general nouns when you've got your specific nouns. So if you've got basically context, don't also put in semantics, would be how I describe that particular rule. But here we've got a knowledge graph for some sort of customer interaction. We've got the customer was born in 1953. So the was born in, I'll show you how I would prefer to represent that using the role and reference grammar layered model. First name, last name is, so those are sentences which we're converting into some sort of label, and that's going to be problematic on scale. And then a customer initiates a purchase, and then a bunch of different labels here occurred at a particular store, which is says Boston, Massachusetts. The customer lives at some particular street, Drury Lane, which is also in Boston, Massachusetts. The problem with that is that it's not that this street is in Boston, Massachusetts. It's that the context is that street is in Boston, Massachusetts at a particular location, and you should specify as much detail as you have. If I say I want to fly to New York, no system's going to sell me a ticket to New York. It's going to ask me what airport I want to go to, and I need to specify the details of things during the transaction. So I've got no problem with storing things generically. Like if you were born in 53, that's great, but probably as a human being, you'd say what day, so that you've got the specific detail behind it. Nothing wrong with storing generic, but not ideal. And then here, this is the knowledge graph from hell, I would argue. It's about the state of Maine, and you've got the USA as a region of New England. Maine is a part of New England. You're describing something visual now in language. Nothing particularly wrong with that, although it's an exceedingly large graph to populate fully. Okay, another question, Mr. Marlowe. An article or document is a store of its own graph, but is that a partial of all stored representations, or the whole KG only needed at the time of coding? So yeah, you can definitely work within context. So there's a concept called, we normally think of it, we're having a conversation, so something's in context. That's known in the semanticist world as the context of utterance. So there's the information available at this point. And the context of utterance is then stored in a thing called immediate common ground. So our conversation, this particular meeting that we're having now, the immediate common ground would be all the things I've talked about in this meeting. But you can then take that and archive it into what's called general common ground, and that general common ground is your long-term storage. So human beings are quite capable of navigating in immediate common ground without having to have access to absolutely everything that's gone on in our history. But when new concepts are introduced, you do have to go and fetch those and provide access. So that would be a very interesting environment to be operating in, where you've got this corporate data and you are bringing things in on the fly to then complete the representation. Okay, so let's keep moving. So there's some questions about the correct way of using these types of systems. As I said, there's obviously corporate systems that are extremely accurate at what they do using this type of knowledge graph technology. And I'm sure that the knowledge graph technology is not only to support deep learning applications, it's also for improved management of information. Pattern theory, just because all of this is coming back to either pattern brain theory or role and reference grammar, linguistics theory. In pattern theory, you only can ever store something once. In order to get rid of the processing engine that you otherwise need, the idea is to simply store the information once. If you find the same thing that you're storing again, you just use that particular node already. And the generic examples would be, if I've got the letter A and I know what the letter A means and I see a different way of writing it, I'm going to associate to that different way of writing it and store that as a letter A for future possible comparisons. I'm not going to create another letter A and then have some type of search algorithm to say, I've got this symbol, is it an A, is it a B, is it a C, and then have a big processing engine. So that's one of our techniques for simplifying what a brain needs to do. These three examples really stress the difference between context and semantics. So here, if you can see that, okay, we've got Lassie, Snoopy, Garfield, Felix, and Tweety. That's our particular context. And then we say Tweety is a canary, and then canaries are birds and animals. So there's our traditional taxonomy, our traditional semantic representation. And it feels pretty uncomfortable to me to say Tweety is an animal. And the reason for that is Tweety is kind of a canary, but he's also a cartoon, as are Garfield. Felix is, I think Felix is a cartoon as well. So because they're not really cats, they're cartoon cats, there is some different representation that should take place. And so these things tend to break once you've oversimplified your semantic model. There needs to be something tying it back to context. Otherwise, you've just got a very generic model. And in pattern theory, the specific defines the general because the brain only receives specific information. And in computer software, the general defines the specific because that's how we've always done it. Let's have a look at a couple more examples. Here's a semantic network where Tony owns an iPhone and iPhone is a telephone. Immediately, I don't like that because iPhone is a generic brand of products. There's lots of iPhones, and it's really a smartphone, not a telephone, because there's all these functionalities for internet access and messaging and stuff. So yes, it is a telephone, but you need to have these other elements being shown or somehow represented. So immediately by hitting a set of things, an iPhone, you then get into conflicts with the rest of your semantic network. So somehow it would be better if we could start with a context network and then work out where the semantics are that give us commonality and generalization. Down here, this is, I think these two examples came out of the Gary Marcus book, the Rebooting AI book. You can see here Michael Jordan, and I think the next slide covers this one in a bit more detail, but he's on the Chicago Bulls team, and he's on the Washington Wizards team, which is great. Okay, so here's just a bit of an expansion of the notes. So Michael Jordan was at the Chicago Bulls, but notice here he was there from 84 to 93 and then from 95 to 98. And I think he took a couple of years off for some reason in the middle of that. And then in 2001 to 2003, he was at the Washington Wizards. But the other thing is that Michael Jordan's the famous professor at Berkeley that explains the three different types of AI that people talk about. Human imitative AI, which is the area that I'm focused on, and then infrastructure AI, which is the one where you're optimizing search or you're optimizing the car path from New York to San Francisco. So that when we say Michael Jordan, you're immediately stuck that you have to, as a person would do, which Michael Jordan do you mean? Oh, the basketball player, okay. And now the rest of it makes sense. So you have to ground your context somehow. And language forces us to do that. But also here, I'm showing these layered models, the Roland reference grammar model, where the basic predicate and its arguments are being grounded in space and time. Chicago Bulls isn't really the place, but we'll just work with that for the moment. And then the time, so place and time is grounded it. So you then finish up with three separate representations, but interestingly, it's the same main predicate there. So the generalization can come from the fact that we're only storing, as in that previous question, the MJ plays basketball is stored once, and then you've got three separate elements which are different surrounding it. One is the date and time, and the other is the team. So, object-oriented programming doesn't scale. Yeah, you'll have to explain a bit more of that to me, Steve, because I mean, the application I showed is object-oriented. It's quite annoying to have to code with pattern theory because we can't make use of a lot of the object-oriented benefits. But yeah, I'd like to understand why OO didn't scale before 2012 and why it does now. So here's the industry. I'm stealing the approach that IBM used in the 1960s. So they bet their company that they can build a computer that follows a particular architecture. And System 360 architecture then worked really well for 10 years and basically set the platform for IBM to dominate for the next 30 years or so until the PC revolution came out. And so in System 360, you've got your architecture specifications. You may not like the fact that the way they do addition is, loading register 1 and 2 and then storing the result in register 1. You may not like that, but that's the spec. So if you write software that works to that spec, it's going to produce an answer. And if you then get a team of 1,000 people to write some software for an accounting package in 4 years' time, because the architecture is unchanged, your System 360 architecture, you can keep upgrading your CPU and the system's going to perform exactly the same, and you've got effectively investment protection. So if we apply that to the NLU industry and knowledge graphs in particular, if we start to store meaning representations in our super knowledge graph rather than English words for an English system, and we have a specification that says this is how it's going to always work, then while the specification's valid, it's always going to produce the results that we expect. And so moving from the focus on data-driven systems to one which is very analytical and symbolic, this new NLU system is going to operate for the next 1,000 years by simply taking a meaning repository and then using a specifications to produce the same thing every time. And the only way you can tell when you've got a very large language system, which has such exponential numbers of permutations in it. But by having accurate tests for all of the classes, you then know that you're obeying your spec. So as long as the spec stays the same and your tests are all passing, you can keep releasing systems and knowing it's going to produce the same thing every time. If you don't like the spec, then change the spec. So that's the concept of the next NLU industry. The other pieces, and I've got a clearer diagram on this, but I'll repeat it. So you want as many languages as possible to be matched and stored in the super knowledge graph, and it should be automated because there's so many moving parts. It would be very hard not to automate this. And then as many languages being generated out as possible, so that your semantic representation, if it's got attributes that are being tracked, then we want to retain those. So my plan is to have in 2023 a steering committee set up where we start working through these specs and agreeing what's going to be in them. Should it be called a context graph? Look, that's a fantastic point. You don't store a word in the graph. You store. Yes, so I'll show you a detailed diagram shortly where you can actually see the moving pieces. But that's an excellent point. Why don't we call it a context graph? I think because the industry calls it a semantic one. So great point. We'll fix that. And universal, so stored in English can be recalled. Yes. So the universality comes from the fact that we're converting from a specific language to meaning, and that meaning representation is lossless. So new industry overview. Oh, let's see. I think there'll likely be multiple standards or communities of practice, but in due time, these are not robust. Those that are not robust will fall away. Yeah, sure. And I mean, so the best way for science and engineering to progress is try something. When it doesn't work, inevitably there's going to be aspects that don't work properly. Well, go and change them. So the closed loop here is having a specification that you're building this off, but there's no reason that we have to have only one. I think in practice, competition is going to mean that you're going to have a whole bunch of these. But the principles that I'm outlaying here apply at least in terms of role and reference grammar, what semanticists would say that aligns with role and reference grammar, and then pattern brain theory. But potentially this could work with some sort of computational engine or deep learning engine or something else. Just haven't seen how you'd do that yet. So here's the architecture view, bit of an old diagram, but you can see in terms of how you interact with users. The users sit up here, so they're either coming through with speech, text entry, and they're getting output. So there can be any type of front-end system sitting over here. And then what this is accessing is the meaning matcher, which I think I've shown you, the conversation engine, which I have. There's another one here, which is our goal-directed conversation engine. And then in the middle here, we've got elements relating to a goal-directed conversation example where the customer, the developer, controls the context of their customers and the unique environment that they operate in. Because perhaps a company has special products. If you're Apple, you'll have your iPhone 10, 11, 12, 13, ABC, however that works. So you might want to have a developer that's working with something that the generic world can't have. I think ideally you want to have one thumping big repository out there that covers everything, so that everybody can take advantage of the same language, the same elements. But that's a commercial question of the future. And then dialogue templates is how you can handle goal direction to get to a point. Let me just jump back. I'll show you these I'll illustrate them better. And then at the bottom here, we've got a language loading interface where we're storing our predicates and reference. So predicates being the elements that relate other elements in the system, and reference being the things that we're manipulating, as opposed to nouns and verbs, because nouns and verbs actually fit into both categories ambiguously, and is very unpleasant to have to work with, particularly with parsers and the like, as we saw from lack of progress from 1960 to about 1990. And then multiple languages can fit in here too. So there's better examples of how that fits together. So in that system, just looking at it another way, we've got language-specific elements here in blue on the left. So you can have as many languages as you've set up, and in there you've got the vocabulary and phrases that relate to that particular language. And in the semiotics model, those are your signs. Then there's this semantics element, the word senses, which is your dictionary definitions. They're not like real dictionary definitions where you've got the ambiguity in the words that define them. We've just got associations defining it. And then we can connect from the senses into the super knowledge graph, which is building out of these word senses and other attributes of the meaning side of things. So the language independent elements are these green bits on the right, and the language specific elements are the blue bits on the right. And there's no reason you couldn't just keep adding languages forever once you've got enough of the super knowledge graph working that's then compatible without having to make changes to anything else. And then notice here on the context side, we've got New York Times, Wall Street Journal, etc., magazines, books, where you're storing the meaning of those in the central repository and then pulling them back through the system to generate it into a target language, because the system's bi-directional. And I mentioned before immediate common ground and general common ground. So the immediate common ground is your conversation. And Brett Forbes is the super knowledge graph guru that, or the knowledge graph guru I've been working with, where we're taking the representation of the meaning and then storing it in a super knowledge graph. So for this system to interact with that, we're using a JSON interface, so it's pretty generic. Okay, so before we get into theory, I'll answer this question. Object-oriented programming is not dynamic enough. DL, is that OOP, object-oriented programming? DL just captures more than you could do with an expert system. Not better, just larger and thus more usable. Okay. So, yeah, the dynamism is interesting. The reason the system that we're using scales so effectively is so this all kicked off in 2006. And I was properly trained with how to design a parser, and I was looking at nouns and verbs and wondering how you could possibly take something as ambiguous as a noun and make it work without getting this big combinatorial explosion. So I removed the parts of speech from the system and just started working with simpler elements, a decomposition, which now has become the semantic predicate and referent, and then the elements around it. So the meaning-based engine built in 2006 is exactly the same engine that's driving things now. There's been no need for change of any of that. So the object-oriented programming that drives the system of pattern matching is very simple. So as a result, the only things that we're using object programming for is the specific classes as we keep refining to get a simpler and simpler model of English is the bit that we're focused on at the moment. Connor, how will Pat handle company-specific language versus general language in cases where a company has a unique meaning for an already common word? So when we're entering into the system, the disambiguation works in a reasonably straightforward way. If you've got a predicate that allows particular arguments, then the predicate can only match those arguments. So if you've got a particular word where, iPhone 10, it's a type of iPhone, which is probably a type of smartphone, which is probably a type of telephone. Inside there, if you're talking about speaking on the phone, then the device that you can speak on, the tool where you're talking, will be in a category which might have a hypernym of, say, smartphone. So if smartphone was the element, then everything that sits below it is going to work correctly with that interpretation. I don't think we create, even in the corporate world, words that are the same as a generic word that's used the same way. We recently added a bunch of people's names, and one of the names was Happy, and obviously Happy is also a predicate, but in the case of a referent, you don't use the same sentence construction. So Happy is here isn't going to work where Happy is a predicate. It'll only work with a name and so on. But the main point is that we want our testing to align with the vocabulary. So if you've got a bunch of special words that you think are potentially going to cause problems, then make sure that they pass all of the tests first and resolve those prior to going live. And let me just pop back to this system, to the demo, and just make one more point. So here is a conversation. If I can click on it properly, I'll just run them all because of time. So we've got the word fed here. So if you feed something, basically you're causing something to eat. So there's 3 roles that are involved. And so we've got a man and a policeman operating. I'm pretty sure this wasn't the one I just did. And so the point is that all of these questions are being answered on the right-hand side as we ask them. And there was only one statement made, which was the policeman fed the man the pizza. So if we look at the current context, we've broken it down into that means this. The policeman does something which causes, the man to eat pizza, and at the end of that, the pizza's been consumed. So that's what's called active accomplishment in ROG. And if we looked at the full detail of the meaning matcher, you can see that we've generated that as the result of the meaning of feed. And then we've got the arguments that are being linked correctly per the role and reference grammar algorithm. But the other point, and I was talking about Brett Forbes as the knowledge graph guru that has done this particular work for us. If we look at the JSON export, we're simply producing the same information that you're seeing on that screen. So we know that that was a statement that was added. It was past tense. It was positive. So it wasn't the policeman didn't feed the man the pizza. We've got a particular word sense of do, which is this is the unspecified activity. We know it's an activity. It's got 2 roles. So all of this stuff, the policeman, it has a meaning of R:policeman. It's a count. You can have policeman or policemen. So all of this stuff is being shown in that particular feed. And the reason that's relevant is if we go back to that other image, back to this slide, what Brett's been able to do is take both the word senses and the super knowledge graph representation, store them both in the Vatical type DB environment, and that was the basis for that proof of concept. Steve, so you're using object-oriented programming to navigate over properties of stored data, which are well known, not to manipulate the data itself. Yeah, that's right. So the meaning engine takes phrase patterns and it's applying them to the particular sentence in order to make sense of it. Let me show you that because I haven't done that on this stream. Just to prove that there's no magic going on here. If we go to the meaning engine and let me just upload the text of that last example. So if we analyze that one, I'm going to give you the phrase breakdown. The policeman fed the man the pizza. So the work is being done by the pattern matching engine. And what I'm showing here is we've recognized those words. Sometimes you can recognize multiple words for these positions, but all of the patterns that match from the word the are being shown in this first box. So when I click on that, you can see we're slowly building up the whole sentence representation. And one of the breakthrough approaches we found was if you match your syntax independently to your semantics, then you finish up with semantics validating syntax, and that way it just reduces the complexity of building the system. So things like this one, ATY, that phrase name I just happen to know is an activity, which is a semantic set. Things like this are syntactic elements where we've recognized the policeman fed the man, and now we're adding the pizza, which is another referent being added on to this syntax set. If we then click on the policeman fed this final view, then this was the best choice that we then surface. Because obviously if you haven't matched all the words, it's probably not the intent of that particular utterance. Hey John, so if we want to use feed in the context of an internet feed, a reference, Pat would separate them, one as predicate. Exactly. So internet feed is either co-location or a standard connection, and feed plus internet has to be the same meaning. Ideally, I'd like to see a semanticist go through that and say, well, is feed in that case the same type of feed or a different one? When I did the analysis for run, which you would think is a pretty basic one, you then start to find the other uses of run, like water can run, wax can run, as in flow. Geez, maybe I don't speak English well. You can, you can run a company. So all of the different uses of run, you start to think, well, maybe it's just some sort of motion. And if we just store run meaning that and we disambiguate, then you still get the same result, but you're simplifying your model quite a bit. And so I'm all up for doing as much of that as possible. In the example which I showed earlier, which was the buy, sell, pay, we'd had discussions with guys at LinkedIn who'd previously worked for eBay, and those guys were saying that they'd had the most horrendous experience you could possibly imagine, where they'd how are we going for time? We're going over. Where they'd worked on multiple languages to try and do the different ways of paying and recognize it with an NLP engine at the time. And they were just pulling their hair out because they said there were like 15,000 ways they worked out that you could pay for something. And I suspect that's a lowball number. And in that example that we showed between buy, pay, sell, rent, all of those pretty much fit into the one model. Okay, so because we're running over time, I'm just going to explain what the rest of this is, so that at least we've got the record of it in YouTube. So here's some theoretical components. The Grice's maxim is a philosophical concept. The question is, what is this thing? And the argument is that everybody on the call is saying it's a lion. And that nobody on the call is saying it's a lion walking to the left, or it's a male lion, or it's a non-female lion, or it's a picture of a lion. All of those things are valid interpretations of this. Dog with a bad haircut, cool. So the reason people say it's a lion is because of these Grice's maxim. So when people communicate, they use these things, provide as much information as required. So for me, the reason you say it's a lion is because it's providing enough information to say what that's a picture of. And if somebody's got more detail, or there's a different context, what is this, a picture or a photograph? Well, okay, then that forces you to answer differently. So role and reference grammar versus knowledge graphs. Because of time, I think probably the best thing is the best thing is to keep going, because otherwise we're going to be 3 or 4 hours up. So the general defines the specific. So as a programmer, you would write your little template and you'd force people to fit into that. So that's the general requirement defining the specific information. So here is a typical form. We've got name field, etc. So if you happen to be Pablo Picasso and you come up to this, even though he's not alive, that's his full name, and you'd see first and last name and you'd be very disappointed you couldn't possibly fit your name into it. And then here there's some tags, and the tags are showing us that there's a desktop, laptop, PC, but there's no option for an iPad or a Galaxy tablet. So that's a case of the general form defining the specific requirements. But if we take this example here, this comes out of the Loebner book. Which of these are cups, bowls, and vases? And potentially they all would fit that depending on how it's being used. But the idea of the specific defining the general is, if you saw that object and somebody called it a vase, you would then be able to do that association. And no matter how many times people call things of different names, you're simply associating those so that when you've got a specific element in context, you can resolve it. The role and reference grammar categories. This is a very interesting view of these layered models, where in a layered model you basically got your nucleus surrounded by your arguments, and then surrounded by when, where, and why. And the interesting part is that the nucleus, the central piece, can be virtually anything. It can be a noun, an adjective, a verb. It can be where, when, why. So all of those examples, the nucleus is one of those things. But when we cast it into this one on the circle on the left is the layered structure, a simplified layered structure, where the nucleus is any of those elements. But the thing on the right is a representation to store into a semantic network, and that does have the when and where surrounding the elements in the middle. So if John is at the beach, John is this central piece, and the non-argument, the location, is at the beach. If it's the party is late, the party is the central concept, and late is the when layer. An example, I showed this in one of the articles. If you had this example, Alan Turing was born on 23rd of June 1912 in London, England. The layered model would say the Turing was born element, the verb piece, sits in the middle, surrounded by the date, 23rd of June 1912, surrounded by the place, Maidenvale, London, England. But the way people speak is you can say, my birth date was this. I was born then on a particular date. And that's basically merging multiple layers of the semantic model. But rather than fall for the trap of simply storing how we speak in English, decompose it into the layered model from Roland reference grammar and store that, because then you can easily generate it into he was born on this date, rather than being constrained by birth date, which then creates an explosion of possible semantic representations. What's in a semantic network? Here's our hypernyms at the top. An animal, a dog is a type of animal, a basset, hound is a type of dog, and then meronyms or holonyms, depending which way you go. On a human body, you've got a head, you've got two ears, you've got one face, you've got two eyes. So all of those things combine together. And I think if we were to focus, well, we're showing it, if you focus on simply these associations and the extra one relating to the selection or restriction, so the constraints of the verb, then that's sufficient to store enough to recognize language. How do we build this thing? The last element is this context of utterance concept. So this comes out of the Sebastian Loebner book. And interestingly, it's pretty much identical to the J.R. Firth model from the 1950s. So when you talk about something in context, there's the speaker, there's the other people that are involved, there's the place that it takes, and then there's the content. So if we convert that into the concept of the New York Times article being stored as a meaning repository, the context of utterance is pretty much the New York Times at some web location with the content, which is their particular article. So it aligns very nicely with semantics theory. And I think that's probably the last step for today, because we are out of time. This is just looking at the specific semiotics model. So this is how it's being implemented. If you've got the concept of destroy, which is a predicate, and there's not that many predicates, you can have these verbal forms like destroy and destroying, which have a bunch of attributes, but they basically got one meaning, which is this predicate of destroy. And you can have noun forms as well, which are the nominal forms, destruction and destroying. They've got their own attributes. Notice everything, all of the attributes is on the meaning side. The only thing that's not on the meaning side are the word forms, the signs, because the signs have no meaning. And today's technology tends to focus only on signs and the statistics around it. But by moving to this model, we're getting a lot more power. And what's the meaning of a particular sentence? Well, this is the Vandals destroyed the city. And notice that we've got this concept here of destroyer, which is the person who destroys, and ruins, which is the thing destroyed. So those are very closely related to predicates as well. So we have to focus on the things of the world and then the things which are directly related to predicates in order to make this effective. Okay, so I think that's probably a good place to wind up, just at about the hour mark. I'm happy to take a couple more questions now, but Okay, thanks, John. Some of the questions we didn't get to I can answer after the session, or we can possibly just run another video to run through them. Yeah, okay. So thanks very much. I'll be posting a bunch of the links, of which these were the ones that I had referenced in the comment section of the YouTube video. And thanks also to Beth Carey today for doing the excellent moderation. Well done. Okay, so we'll leave it there. Thanks for joining me today. Hope to see you all on the interwebs in the future. Bye for now.